All right, so property-based testing, that's what I'm going to talk about today. My name is Andrea. I moved the mic, yes. I'm in the Elixir core team. I've been working on property-based testing for the last few months. I work at a company called Weed Maps, as in weed, like weed. So Weed Maps is it's like Yelp for weed. So you can just, yeah, it's a true story. So in places where it's legal, I said into the mic, so they have reviews for dispensaries, and you can find dispensaries close to you and doctors that prescribe, and you can review weed. That's it. It's a really great company. So I'm working with Elixir there. We have a lot of Elixir going on. We're running a lot of new stuff with Elixir, and we are hiring. So if you want to come work at Weedmaps, which surprisingly doesn't include weed, I mean, this is true. You will have to program like any other job, then just go to Weedmaps/careers. So let's start talking about testing. So basically, why do we test our code? We test because if there are no tests, then we have not a lot of confidence in our code. We don't have a confidence in changing our code, because every time we want to test something, we have to do it manually, and it takes time, and it's error-prone. So we're not confident in doing changes. We're not confident in our code. We're not confident in doing additions. So we do testing of our code so that we gain confidence in our code, basically. And with tests, we're basically more confident that when we change our code, it won't break, that the known regression cases are covered, and that everything works, and we don't break anything. And probably the most common way of doing tests, or the most diffuse way, is unit tests. And unit tests are for testing like small amounts of code, and they usually look something like this, a list in Elixir. So you have a function sort that takes a list of integers and sorts the list of integers. And the unit test for that could look like this. So you would test, for example, an empty list. You would test sorting a sorted list, and you would test sorting an unsorted list, and do expectations on the results. This can be referred to, it can be thought as example-based testing, because you're basically just checking for a bunch of examples your code works. So you're just checking that, for example, for the list with 1, 2, 3, then the code works as I expected. You can also think of this as table-based testing. So you basically have a table of inputs and outputs, inputs and expected outputs, and you just run your code through the table. So you feed it the input, and you assert that you get the expected output back. So unit tests, they're really good for a bunch of things, because they're easy to write, they're usually straightforward to write, they are really good at covering stuff like regressions and known corner cases. Like in the sort example, the empty list would be a known corner case, because it is a list with no elements in it. So it's really easy to cover those known corner cases, because you know them. And it's also, though, hard to do a bunch of stuff with unit tests. For example, finding unknown corner cases, because you don't know them, so you don't know how to express them, and you don't know that they're there. And with unit tests, it's also really hard, usually, to express properties of your code. So if we were to look at the sorting unit test that we saw earlier, it would be really hard to tell that our sort function is a sorting function, except that it's called sort, right? Because, I mean, it's a simple function, it's a simple example, of course, but you can imagine cases where it's really hard to tell what a function is doing just by looking at unit tests for that function. So enter properties. So properties are much harder to write, but they are more, they can be more powerful in some cases. So basically, how properties work is like this. Jose already introduced a bunch of this stuff yesterday, but I'm going to just go through it really quick. So you take you describe a bunch of valid inputs to your code. So you describe the shape of valid inputs to your code, and you define properties that your output should have for those valid inputs. So you define properties that should always be held as long as the input is part of the valid inputs. And then you basically feed the valid input's shape and the properties of the output to a testing framework that will be responsible for generating a lot of valid inputs at random and then running them through your code and asserting that the output has the properties that you expect, that it holds the properties that you expect it to hold. And basically, the testing framework basically tries to prove you wrong. Tries to find an input that you said it's a valid input and that doesn't hold the property that you said it should hold. So for all examples I'm going to show, I'm going to use stream data, which is the library I've been working on for property-based testing in Elixir, and it's what's going to be in Elixir 1.7. So let's start with the same example as before, which is sorting lists. So this was the unit test we had for this. So let's define the valid inputs that the sort can take, right? The valid inputs are just lists of integers. Any list of integers is a valid input to our sorting function. And let's define the properties now that the output of this should have. So the output of the sort function should still be a list. It should still have the same elements as the original list. So you shouldn't add or lose elements. And it should be ordered. So that's the basic properties, some basic properties we can think of. And an actual property for this would look something like this. So you basically define the valid shape of inputs by saying, OK, list of integers are valid inputs. This is a generator. We're going to talk about this later. And then we say, I'm going to bind this to list. So the list would be generated at random on every iteration. Then I can sort the list and have a sorted list. And I can assert the properties that I described. So I can assert that this is a list. It has the same elements as the original list, and that it's sorted. So this is how it would look like if we were to do test-driven development. So like write this test and then write an implementation. We could start with this implementation. So this satisfies 2 out of 3 properties because the output is a list and it has the same elements as the original list, but it doesn't, it's not, of course, sorted, right? So at some point, while generating the random lists of integers, the property-based testing framework would generate something, for example, like this, right? So a list that is not sorted. So this is a list, and it has the same. If you sort it, it will have the same elements. If you sort it with the function I just showed, it will have the same elements as the original one because it will be the same. But it's not sorted, of course. But it's a bit hard to tell that this is not sorted. Or, I mean, imagine that this was a more complex problem and a more complex input. This is not the simplest list that shows that this is not sorted, right? Because there's like large numbers, it has more numbers than necessary, there's negative numbers, and this is all useless to the property that it's not sorted, right? So what most property-based testing frameworks do, and including stream data, is that they will shrink the input that fails to the smallest possible input that still fails the code. So it will try to reduce the complexity of the failing input so that it finds something in this case, like a list with just 2 elements, 1 and 0, which are very small integers, and they still show that the list is not sorted, and the function that doesn't sort the list would break for this as well, and it's really easy to see why, right? It's really easy to see that this is not sorted. So this is the whole like property-based testing, how it looks like. And now I want to talk about a few things that are generators, so how generators work. Then I want to talk about a few patterns that you can use to write properties and come up with properties for your code. And then I want to talk about a little bit about stateful property-based testing, and then about the research we're doing currently in stream data and the future of stream data. So let's start off with generators. So José said a bunch of this stuff yesterday in the keynote, but I'm going to just go through it quickly. So generators are just basically infinite streams of randomly generated data. So if we have an integer generator, for example, and we can take 4 elements out of it, it's just going to return 4 random elements. They're not guaranteed to be unique, because you want to combine generators usually, so uniqueness is not important at all. It's actually good that the values repeat. So this is an infinite stream. I can take as many elements as I want. As José mentioned yesterday, the elements grow in complexity as I keep getting them out of the generator usually, so that this is done so that property-based tests can grow in complexity, so that data grows in complexity when you're testing it, input grows in complexity. And generators are composable, so someone asked yesterday, how do you compose generators, how do you create your own generators, and that's through composition. So we have other generators, like one-off in this example, that take other generators and compose them into new generators. So for example, you have the integer generator, the float generator. If you wanted a number generator that generates integers or floats, you could use one-off, an integer or float, and it would return integers or float at random. And then we have other functions that change the output of generators. So for example, map is the simplest one that just takes a generator and then a function and it applies the function to every element generated by the generator. So for example, if this generator would be a generator for non-negative integers, it would just be integer, which generates any integer, but then we map the absolute value and that they're always positive or 0. And we use composition quite extensively in stream data itself as well. So for example, the ASCII string generator is implemented close to this. So we just take an integer in the ASCII range. So that's the ASCII range over there. And then we build a list of these integers. And then we map the list to string function over each list. So basically, we convert the list to a string, and then we have strings. And so the reason why we want generators to compose, of course, is to create more complex generators, but it's also because we can't use stream functions on generators if we use generators in property-based testing. Because if we do, for example, stream.map on a generator, it will work fine if we're taking values out of the generator, but it will not keep shrinkability. So if you want to keep shrinkability, you have to use stream data functions. So the composition also composes shrinkability. So in the example over here, for example, the shrunk value will still be positive. You will never get a shrunk negative value because the absolute function would be mapped to the shrunk value basically as well. And it's nice to know, I think, that the whole, like Jose mentioned yesterday, like we tried to do this in a very functional way where we have very small primitives and build a lot of generators on top of those primitives. And it's just, I just want to show quickly what they are. And the two ones that I think are most important are the constant primitive and the bind filter composition function. And basically, the constant generator just generates the same term every time you invoke it. So you can use it to turn a term into a generator, basically. And the bind filter possibly creates a generator from generated terms. So you have a generator, it generates a value, and you use the new value to create another generator. So you bind the new generator to the old generator, basically. And this is a very contrived example. You can look at it later in the slides. But basically, we're having an integer generator, and then we're binding a function where if the integer is less than 0, we throw it away, so we generate one more. And if the integer is 0 or greater, then we return another generator, which is a list of integer where we map the function that adds an integer. So basically, we generate lists that are where all of integers where all elements are greater than a given integer. Basically, that's the idea. So this is as far as generators go. Now I would like to talk about patterns, which is a very hot topic. I get a lot of questions on how do I write good properties, which is a really hard thing to do because of course it takes practice, but it's just hard to come up with properties and hard to get into the mindset of property-based testing. And I would like to show some patterns that can help when you're writing properties for your code. So the first pattern that I like is circular code. This is a really easy pattern to spot, and it's whenever you have code that looks like this, so where you have some encoding function that encodes a term, and then you have a decoding function that decodes the encoded result, and you're back to the original term. So this is really easy to test with property-based testing, because you're going to have a test. So, for example, this is for JSON encoding, which is exactly this case, and this is taken almost verbatim out of the JSON code base from Michał in the Elixir team. And basically, he's using property-based testing to do exactly what I said. So he's generating strings, and then he's encoding those strings with Unicode escaping, and then asserting that decoding the encoded string goes back to the original string. And Michał said that this helped, this kind of tests helped a lot while building JSON, and he found bugs And I mean, I'm sure Michal's code sucks, so there will be bugs anyways, but at least property-based testing helped. And this is like circular code pattern. The Oracle model pattern is another really common pattern, which is where you have your code, and then you have some other code that behaves the same as your code. And we call that Oracle code, or the Oracle. And this can be an older system, it can be an older system, for example, that you're re-implementing, that you're rewriting, and behaves the same way as a new system, or it can be a less performant implementation of an algorithm, for example, that you know is correct because it's much easier to understand, but it's way less performant. So in those cases, you do something like this, where you just assert that your code behaves in the exact way as the Oracle code does for all valid inputs to both codes. And an example of this that I used recently is when writing an HTTP2 client, and HTTP2 includes some Huffman encoding in it, and there's an Huffman encoding library in Erlang that I couldn't use, but I used it as an Oracle when testing my implementation. So I just basically generate any binary, and I test that my implementation encodes the exact same way as the Erlang implementation. So another pattern that I like, and I heard this in a YouTube talk that is linked at the bottom of the slide, is doing smoke tests with property-based testing. And this is useful because often you have like a large system and you don't know where to introduce property-based testing because you can only introduce it maybe at a very small level, a very low level, and it's really hard to know where you can start using it. So smoke testing, you can use property-based testing to do smoke tests. So an example could be you have a web API, HTTP API, and you know it can only return one of these codes. It can only return either 200, 201 if something went well, or 400 and 404 if there was an error. So what you can do to smoke test this basically is to do a property-based test where you generate random HTTP requests. And then you perform those requests on your system, and then you assert that the resulting response has a status that you expect, basically. So what you're doing here is you're ensuring that you don't get any unexpected things, which is really the point of the smoke test. So you're not ensuring that your system works correctly, of course, because you could generate a response that is supposed to return 200, but it returns 404, and this test would pass anyways. But at least you're asserting that there are no, or at least like you're gaining confidence that there are no HTTP requests that you can craft that will break your system in unexpected ways. So it will let it return like 500 or other status codes that you don't expect. And I think this is really good to like start using property-based testing in large systems. So take like big chunks of the system and just ensure that, like, do smoke tests and ensure that nothing unexpected happens, even if you don't know if actually correct stuff is happening inside. Another pattern that I want to mention really quickly, because it's really simple, is to be very slow, very quick in CI, so use a very few number of iterations when using property-based testing in local development, and bump that number up in CI a lot. So for example, you could have something like this in your configuration where you say, if I'm in a CI environment, I want every property-based test, every check call to run 500 times, so to generate 500 random inputs and test all of those. Otherwise, if I'm developing locally, I want to create 25 random inputs. And this is really good because you want to fast feedback locally. You want to be fast when developing. So you want to tests to run really fast. And 25 inputs is still enough that you cover the space of inputs, at least in a well enough way. And then you run tests locally a lot of times, right? So every time those 25 inputs would be different. So you're still ensuring that you cover enough inputs so that you know you're not breaking anything. But on CI, you can bump that number up because you don't care about the time that CI takes to run your tests, and you can try many more inputs on CI. And then the last pattern that I want to talk about is not a pattern, it's just advice, is don't drop unit tests when you want to work with properties. So properties, I think that properties and unit tests are meant to work together. They're meant to live together. Unit tests are still really, really good at a lot of things that property tests can do. So for example, they're good at known corner cases. So it's hard to cover known corner cases with properties because you have to kind of force the known corner cases to be generated when it's much easier to just basically have unit tests for them. Their unit tests are really, really good for regressions. So if you have a regression and you have a unit test for it, it's better to have a unit test for it because you don't know that your properties are going to generate the same regression. Unit tests are good for spec examples as well. So when you have a specification like Huffman in the example before, there are some examples, and it's good that you test those exact examples, I think, on the actual, as unit tests. So you test those specific examples. And then you have properties for all that other stuff you want to check on your code. And this is an example from yesterday's talk from Jose. So Jose got asked something like this, I think, at the end of his talk, and I don't think he gave an answer, because I don't think he understood the question. But so the idea was that you have something like this, string contains, where you have a property that string contains. If you concatenate two strings, then the string contains returns true for both substrings. And someone asked, like, how do I do a negative case for this in the property? So if I make string contains return true all the time, this is going to pass easily, right? It's just going to work. So the idea, I think, is that you pair this property with another test, which is a unit test, basically, and it just tests some actual data, so that you know that, like, I'm missing a refute here, sorry, but there should be a refute for that, testing that something that is not in the string is not in the string, right? So if you pair the property that tests the general property and then a unit test that basically computes that the property actually doesn't hold for invalid inputs, they live together and they give you basically the best of both worlds. So you're kind of sure that it works for invalid inputs and you're sure that it works for valid inputs. All right, so these were the bunch of patterns you can use when coming up with properties. As I said, coming up with properties is inherently hard, I think, because we're not used to it, but it's very beneficial because it doesn't only let you write properties and test with property-based testing, it also forces you to think about your code in a way that you're not used to, and you think about what are all my valid inputs and what are some properties that should always hold, and you'll find out that oftentimes the property-based testing framework will find inputs that you didn't think were valid, or it will find inputs that you thought were not valid but that actually should be valid, so you have to change your code, and it will help developing software not just by testing it, but by changing your approach to testing it as well. So I would like to talk about stateful testing now, which I just want to talk about it because we don't have anything in stream data yet. But stateful testing is, so if you noticed, everything that I said until now is actually stateless property-based testing. So we're only generating data and that basically doesn't have state. We're only generating terms and then using those terms. Most of the times, though, you have in your system, you have some kind of state. You have some stateful systems, like it could be a chain server, it could be a cache, or anything like that. So those systems are stateful, they have a state. And property-based testing is really, really good at testing those kind of systems, testing stateful systems. So the idea behind stateful property-based testing is that you start with a model. So you model your system in a way that you can express in your code. So that's referred to as the model. And then you have a bunch of valid commands that you know you can execute on your system, and then you will execute them on the model as well and check that the results are coherent, that they're expected. So the model is usually just a state plus a bunch of state transformations. So the state can be a data structure. The transformations are transformations that what you do when you execute a command on the state, and then you have to update the state to reflect the command that has been executed on the stateful system. So this is a state, a bunch of state transformations. Commands, they're a bunch of calls, so they can express calls to your system or commands that you execute on your stateful systems, plus a bunch of preconditions that are used so that you don't execute commands in states where they should not be executed. So for example, if you have a cache or a gen server, you only want to execute the command when the gen server is up, and that would be a precondition on the command that the gen server is up. So that we only generate sequences of valid commands. And then the idea is that you feed these commands and the model to the property-based testing framework. And the property-based testing framework would generate a bunch of commands and then run them both on the model and on the stateful system at the same time. And then every time it runs a command, just check that the stateful system, the some property of the stateful system is reflected in your model. So that's up to you, of course, decide which properties and how the model represents the system. But that's what the property-based testing framework does. And if there's something that goes wrong, it's really, really useful because the commands and the command list will shrink. Just because they're generated from generators, property-based testing generators. So the command list would shrink, and it would try to find a minimal list of commands with simplest possible arguments that if you execute them on your system, they will reproduce an error that you found through your model. And I just want to give a quick example on this. That could be, this is something we're discussing in the stream data repo and in the team, and we're using this example for now, so I thought to use just the same example, so which is just getting a setting keys in Redis. So we want to test that Redis is capable of getting and setting keys. And in our case, the system that we want to test is Redis. I think, okay. And the model that we use is just a map, because it's just a key value store, just as much as Redis for our purposes. So we just use a map to represent Redis in our case. And then we have just two commands, which are get a key from Redis and set a key to a specific value. So implementing the commands for the model is really easy because they're just, since it's a map, we know that like getting a key from a map is just a map get, and setting a key on a map is just a map put. So this works. We can implement this just fine. And then this is just like, of course, it's a made-up API because we don't have an API yet, but this is how it could look like. So when I want to generate commands, I can say, okay, the commands are one of these commands. And each command is going to be, for example, the get command is going to be get and one of the keys that exists. So we have the model on the first line. We know the model, and the model is a map. And if we get the keys from the map, we know that those are the keys that are supposed to be in Redis because our model perfectly reflects Redis. So we can get the keys, and then we can say, for example, a get command is get one of the existing keys. A set command can be just set a random binary to another random binary, set a key which is a random binary to another random binary, or set an existing key to a binary. So the last one would be set existing as semantics go. And they could look something like, so the actual state transformation and assertion that everything work would look something like this. So if you have a get command, you're not changing the state because you're just reading from Redis, so you're not updating your model. But it could look something like this, where you do, okay, check that this getting the key returns an okay result, and then check that the result is the same as the result that we have in the model for the same key. So basically, I want to check that when I get a key from Redis and I get a key from the model, that they're the same, which should always be true. And the second command, we don't care about asserting anything when we're setting a key, but we care about updating the model. So this would be a state transformation. So when you set an existing key to something, then I update the model and I replace the key to something in the model as well, so that basically they're always in sync, or at least the model behaves how I want Redis to behave, and then I can check that Redis behaves that way. So stateful, as I said, stateful property-based testing is really powerful, and it's been used a lot, and it's a lot of success stories that you can go read, and they're really interesting. And one that I really like is one about LevelDB, which is, I think, a Google database for key value storage. And they used property-based testing on LevelDB, stateful property-based testing on LevelDB, and they first found a sequence of 17 calls that would create ghost keys in LevelDB, and this is like a minimal case that reproduced it. So the property-based testing framework found sequence of 17 calls that were like the smallest sequence that could reproduce this, which means like a human wouldn't have never found this, or if we would have stumbled upon the same error, it would be with a much more complex sequence of calls to the database. So they solved this, and then they ran property-based tests again, and then they found a minimal sequence of 33 calls now, which is like twice worse, but it's the same principle, and then they fixed this as well. And these are like, it's really, really hard that you find this, like a human finds this, I think. So it's like really shows that like fuzzy testing and random testing and shrinking then can bring like great results. So this is about it for stateful property-based testing. We're working on defining an API, which I think is one of the hardest part, like a easy-to-use API for stateful property-based testing. And I want to start working on this soon. It will not be in the version of stream data that is included in Elixir, so it will not be in 1.7, but we'll work on it, and it's going to be in stream data at some point, because it's like too useful to miss. And then I want to talk about the research we're doing in stream data. So the first thing I want to talk about is what Jose mentioned yesterday, which is trees. So trees are really hard to implement and generate, because they're really hard to generate with good distributions, basically. So if you have a tree that looks something like this, where you have a tree that is either a leaf or a tuple, so it's a binary tree, a tuple of two trees, and we have functions like size and depth to help analyze this tree. So if we generate a lot of trees, these are the data that I got with that tree. So if the generation size is 10, for example, the average size, so average number of nodes, is only 5, and the max depth is like 2.5. So they're not deep, the trees. And the generation size, if it grows, the average size and max depth don't grow like as well as we would like to. So for example, the average size for a generation size of 1,000 is just 22, and the depth really grows really slowly. So either we have small trees, or we have very flat trees, or we have deep trees that don't have a lot of nodes, where the nodes are distributed in a very vertical way. So as Jose said, this is a really hard problem. So we're reading papers to try to fix this. But for now, it works, but it's not the best implementation. And the other thing, which I'm really excited about, is to basically combine stream data and dialyzer. So this is actually a candidate to be a Google Summer of Code project this year. So there might be a student working on this, which I'm even more excited about. But the idea is that we want to have two things. The first one is to have generators from dialyzer types. So if you have something like this, type timeout, which is a built-in type, which is either the atom infinity or a non-negative integer, then we want to have a function. So this is not a real API, but we want to have a function or something that takes the type, and it will create a generator out of that type. So it will create a generator from the timeout type, and this would be roughly equivalent to something like this. So it would be either infinity or non-negative integer. So it would be able by itself to turn the timeout type into an actual generator that you can use in your tests. And this would be already really cool, because we have a lot of types already defined in Elixir, and defining types is easy. The syntax is really easy to use, so it would be good to have automatic creation of generators from types. But the thing I'm even more excited about would be to use this to build on top of this some automatic typespec property checking. So basically, right now we have typespecs which look like this, and we want to build something where the stream data goes in and says, okay, this function takes a timeout, so I know how to generate timeouts, because I know how to create a generator from a type. And then we want to say, okay, now just feed timeouts to my fun and assert that the result is either OK or error. So we would do this automatically from the spec. So it would look something like this. The generated code will look something like this. So you have check all that any timeout, check that any timeout. Basically, if you pass it to my fun, then the result is either OK or error for that spec. So to do this, we're missing basically checking that something is part of something of a type. So we don't know yet how to check if something is OK or error automatically. That's what we will be working on mostly. But this is huge, because it's smoke tests for free, right? So you're not checking that my fun behaves correctly, but you're checking, because it could return OK when it should return error still, but you're checking that my fun always accepts valid inputs and always returns valid outputs. And this is really, really big, especially if done automatically, because you wouldn't have to do anything except spec your function, which you might already be doing. So we're really excited about this. I hope the Google Summer of Code project goes through and we can make this happen. So in conclusion, just a few parting words. Property-based testing is really nice for a bunch of things. The first thing is to find obscure bugs, because it will generate weird data that you would never try yourself. And it will feed it to your system and find weird bugs. The other one that I really like is that it reduces input to a minimal failing input, so it doesn't just create very weird data that will break your system. It will also take that weird data and make it less weird in order for you to understand why it broke the system in the first place. It's very good at finding specification errors as well, so not just bugs in your system, but as Jose mentioned yesterday as well, finding bugs in protocols and finding bugs in what you think your system is supposed to take, what you think your system is supposed to output or take or don't take. So these kind of things. And then it's really good at covering a very vast input space, because data is generated at random every time you run, and you run the tests many times. So over the time, you're going to try a lot of data against your system, so you gain more and more confidence that your system behaves correctly. So as we said, this is going to be in Elixir 1.7, so I'm really excited that it's going to be in core, because it means that it will be really accessible, easy to use, it will be well documented, and it will be just there for you to use it. So for now, though, just use stream data, so that we can make it stable enough that it's in core, and you can start benefiting from it now. Then use property-based testing anyways. If you're not an Elixir programmer, there's implementation for everything. I know there are for Scala, Java, Clojure, Erlang, Python, JavaScript. There's pretty much for everything. So this is not an Elixir thing. So if you don't use Elixir, you can use property-based testing anyways. And that's it.
Thanks for the talk. I was wondering, what's the difference between the stateful testing that you showed and the approach when you can just generate different things and use pattern matching to call the function dynamically, or just send a message to the gen server? Because I don't know if there's any difference, and maybe I missed something.
So I'm going to try an answer to the question that I understood, but then you can talk to me later if the question, I didn't understand the question, but the idea is that if you want to, for example, you can definitely generate random messages to send to a gen server, and that's going to work without stateful testing. The problem is that usually the problem is that you don't have a model to check against on every step, so on every command that you take, command that you issue, so it's really useful to have that built in the framework. And then it's really hard to generate valid lists. No, it's not really hard, but it's hard to generate valid lists of commands that you can execute one after the other and shrink that in a way that they remain a valid list of commands. So that's where the stateful property-based testing would help. I mean, I think mostly it's just a matter of a good API that expresses the tests and the properties well. Yep.
Hi, so I was wondering, you mentioned that property-based testing is really good at finding inputs that are accepted but shouldn't be. How would you kind of code that? How would you recognize them? Because if you're asserting on the function returning true, then how do you know that it's actually not valid?
In many cases you can't recognize that like you're testing more inputs than you should, but in many cases as well you test an input that you didn't think your system should take, or that you thought your system didn't take, and it takes it, and it actually behaves in a weird way that is not expected, and that's how you or either it breaks or it just behaves in a way that you were not expecting it to behave, and you kind of guess it then the input wasn't valid or is valid, you just didn't handle it, basically.
Do you get some sort of output in that situation, or do you kind of have to guess that?
Oh no, you would have to. Yeah, you would have to guess. Yeah. We have no tooling for like this kind of stuff. I mean, you would just have to. Yeah, depending on the system. Yeah.
Cool. Thank you.
Hi. Thank you for the part about patterns, because that's really useful. And while you were talking about the smoke test, especially, I was thinking, like, how does the shrinkage work if your system is a little bit flaky?
So I'm going to answer a question, which is like, what if the system, when shrinking, fails for another reason? Is that a? Yeah.
So you it comes up with an example input. The system fails, and you start to try to shrink, but then you can't reproduce the error while shrinking. Like, does the shrinker become confused?
So the shrinker. So first of all, it will not look for the same error. It will look for any error, like going down on the data, right? So if the data, if the error changes, so for example, if you have, in that case, if you find a state, like a response status that is not in those 4, so you find an input that causes that, right? Then it starts shrinking it, and at some point it finds exception is raised, so the response is returned at all. It will still consider that an error and keep going down. So whenever the test doesn't pass, so assertions fail or an exception is raised, so whenever the test doesn't pass, it will consider that as a failure and keep shrinking on that, right? And if it doesn't find any error when shrinking, it just reports, I couldn't shrink anything. I mean, this is the smallest data. It tries to find it doesn't try to find the smallest data. It tries to find a smaller smaller version of the data that caused of the input that caused the failure. And if it can't, it just reports the original one.
All right. Okay. Thank you. So the last thing you said about generating property tests from type specs. What actually is the difference from just running the type check? Like what extra do you get by doing this?
I mean, if dialyzer worked perfectly, it wouldn't change anything. But dialyzer is weird to run, and this is a dynamic language, so I mean, it's good to test it for actually running it, and yeah, that's it, I guess.
Yes, I understand the value of testing, but in our system, the test might take more than half an hour, sometimes an hour, to go through the whole system. What would you expect the performance degradation be if you start applying this?
So the performance of property-based tests?
Yes.
It's terrible, because you're doing a lot of tests. So, I mean, it's not. So if you have one unit test, you're doing one unit test. If you have a property-based test, you're doing that one unit test a lot of times. And on top of that, you're generating data, and you're generating data that is shrinkable, so the performance is not the best. So that's why I suggested that you keep the number of data that you test locally very, very low, so that you can only test a few data locally, but many times, and then use stuff like CI for running a lot of generated test cases. Basically, that's my suggestion.
Let's take one more question.
Thank you for the talk. You said about smoke test and request generator, and I'm wondering if the request generator generates totally random requests, or can I specify, for example, list of endpoints, or?
Oh, the example where I used randomly generated HTTP requests was really made up. So there's no HTTP request generator in existence that I know. You would have to write that yourself based on your system, and yeah, you would have to provide that yourself.
Okay, thank you.
Right, thank you everyone. Thank you, Andrea. Let's give him a closing round of applause.